Welcome back, everyone, to this lecture discussion on evaluating residuals. Often for linear regression, it's a good idea to separately evaluate residuals. Recall the residual is just the error between the true y minus your predicted y hat, instead of just calculating performance metrics like root mean squared error. We just learned in the previous lecture about performance metrics that fall for any regression task. What we're talking about right now is actually specific to linear regression. Linear regression sometimes is actually not appropriate depending on the dataset. So let's explore how actually visualizing a residual plot can help us determine whether or not linear regression was appropriate for our dataset. Recall that we have Anscombe's quartet as a set of 4 different sets of data points, and each of these actually has very similar summary statistics. For each of these 4 datasets, we actually have the exact same mean as well as the exact same variance. And then also we can visualize here that if you were to calculate the linear regression line of best fit, it's the same for all 4 datasets. It's all y equals 3 plus 0.5 times x. So what's interesting here is just mathematically, if you were to take a look at the summary statistics of the data points themselves, they would all look exactly the same. It's not until you plot them against the best fit regression line that you can tell that some of these are not suitable for linear regression. So clearly, linear regression is not suitable for 3 of these because either we're trying to fit to something that's actually a curve, or we're trying to fit to something but we have 1 point way off, or a lot of points stacked on top of each other. So what we're going to do is try to understand how can we tell if we're dealing with more than one x feature whether or not linear regression was valid. Here, it's really easy to tell, but we're limited to one feature. I'm just plotting y versus x, and since I have a single feature, I can very easily just tell visually that for 3 of these, this line doesn't really make sense as an appropriate fit. But we can't actually see this discrepancy of fit visually if we have multiple features. I'm limited by just the different plots and the fact that we live in a 3-dimensional world. If I have 8 different x features, I'm not going to be able to create one of those plots of y versus x and understand if I'm dealing with a good best fit line. What we could do, however, that's going to be able to scale to any number of features is plotting the residual error against the true y values. First, let's consider what this would look like for an appropriate dataset for linear regression. Here, I can see my best fit line against my data points. And it's pretty obvious that linear regression is a valid choice here. We can see that more or less we're fitting to the general trend with our best fit line, and there's no extreme discrepancies in error for any of these points. So the residual errors in general should be random and close to a normal distribution. Here we have again that same best fit line and then a marker for the residual errors themselves. If I were to just actually check out the distribution of the errors, that is the distance from the true y point to my y hat line of best fit, I should get something that looks normally distributed. And recall that if I had an absolute perfect fit and I was hitting every single line, then my residuals would be very close to 0. So we hope that the residuals themselves, when distributed, are close to a mean of 0 because we want them to be centered around 0 since 0 indicates a perfect fit. And realistically, we're not going to get a perfect fit, so they start getting distributed a little bit to the negative where we overshoot and a little bit to the positive where we undershoot. I can expand on this idea of checking my residuals by not just plotting their distribution, but plotting the raw residual points themselves against the y true value. So what is this actually showing us? On the y-axis, I have the residual. Note that it's typical to have a horizontal line at 0. So if I had a perfect fit and I was hitting every single data point and there was no errors, then I would expect all these blue points of the residual to be right on that red dotted line. But obviously, we're not going to have a real perfect fit for real-world data sets. But if I know that I'm more or less hitting a data set and overshooting some of them, undershooting others, then this actual residual plot should pretty much be random. There shouldn't be any clear line or curve, and I should see about as many points above 0 as below 0. That way I know there's not some extreme discrepancy for any particular data point. So keep in mind that all we're doing here is residual versus y value, that is the y true value. which means I'm not actually considering any number of features. So I should be able to scale this particular residual plot to any number of features. So what about on non-valid datasets? Here, we clearly have some troubled datasets. What would their residual plots look like? Let's calculate it. So let's first take a look at this one. Here, we have a straight linear fit on something that should probably be a curve. It almost looks parabolic. So what do the residuals look like? Well, here we're showing the 3 different plots we can do. The first one is limiting because it implies we only have one feature, but it's just showing you the line of best fit and then the distance to the actual residuals themselves. And then the one in the middle is showing you the distribution of residuals. You can already see it's a little suspicious because while it does appear to more or less be around the 0 mean, it doesn't look exactly normally distributed. However, the real indicator, and this is the clear one, is the residual plot itself. Here, there is a clear curve or pattern within the residual plot, and this should be ringing alarm bells of the fact that this dataset itself is not valid for linear regression. If you get a residual plot that looks like this, regardless of how many features you're considering, you know that there's something strange going along with the underlying dataset. It may not be easy to actually visualize a curve, since you may be dealing with multiple dimensions, but this residual plot, if you see a pattern like this, is indicating to you that the dataset is not valid for linear regression, and you should choose another model. And obviously, later on, we'll discover and learn about other models beyond just straight linear regression. So let's check out what it would look like on this non-valid dataset. So here, we're getting the same best fit line, but obviously, trying to do a best fit line to this particular dataset is not really a valid choice. In fact, it almost looks like some sort of classification problem where the values are either 8 or like 19. So what happens if we run the same plots? Well, again, the plot on the left is showing us the residuals compared to the best fit line. And what's interesting is just actually running a distribution plot for the residuals will not reveal this data problem, because you'll notice it looks like it's centered right around 0 perfectly, and it's also normally distributed. So it's not until we actually check out the residual versus the y plot that we can see there's a clear pattern. There's a straight line running in your residual, which doesn't look random at all, which again indicates that linear regression was not a valid choice for this particular data set. Let's explore actually creating these plots with Python and our model results. So we're going to explore if our data set of advertising was actually valid for our particular linear regression model. All right, here we are back at the Jupyter Notebook. Recall in the previous lecture, we calculated performance metrics like root mean squared error and mean absolute error. What I want to do now is understand if the underlying data set was a valid data set for linear regression and there was no strange pattern that I couldn't see in some multiple dimensional level. So what I can do is simply plot out the residuals against the y test values. Recall that I have already my test predictions, which means to calculate my test residuals, all I need to do is say y test minus test predictions. And now I have my set of residuals on the test dataset. So I can say test residuals, and if I had a perfect model, then I would expect all of these to be 0. Obviously, we don't have a perfect model since we're dealing with kind of real data here. Instead, I should see some negative values where I overestimated and then some positive values where I underestimated. And these are all just the errors that my model had. Again, these are the residuals for this test set. What we're going to do now is actually plot these out to make sure there's no clear pattern or line or curve within the residual plot. We'll say SNS.scatterplot, and I can actually pass in the data as is. I'll have the x-axis be my y test points, so those are the correct y values, and then I'll pass in, for the y-axis, my residuals for each of those points. So essentially what I should have is kind of this range of true y values on the x-axis, and then an exploration of how far off I am for each of those points. So when I plot this out, you should get something that more or less looks random. There's no clear line or curve like we saw for the Anscombe's quartet issue data sets. Instead, this more or less looks random, and sometimes what people like to do is they plot out a horizontal line on this, and you can do this with Matplotlib axh line, which says along that axis draw a horizontal line, and you draw it at 0, since a 0 line would indicate a perfect fit. And let's go ahead and say the color is red, and if I want, I can also say line style is dashed. That should be in quotes. There we go. And so here we have this typical residual plot. And again, what we're looking for here is to make sure there's no clear line or curve. That would indicate that something funky is going on with the data set underneath, and I should probably not use linear regression. This should more or less look random, and hopefully it should also look distributed around 0. And we can also check this out with a distribution plot. I could say SNS this plot, and then have my test residuals, choose some number of bins if I wanted to, and then maybe even have a KDE equal to true. Run that, and more or less what we're looking for is something that's normally distributed. It looks like the mean is pretty close to 0 for this KDE. It does look like we overshoot a little bit, but having it skewed a little bit one way or the other isn't too bad. Again, the main plot that's going to reveal an issue with the underlying data set is this residual plot, especially if you see a really strong indication of a curve or a straight line or something parabolic. It should look random. Okay, so that is the ability to use residual plots to make sure that the underlying data set is a valid choice. And finally, the last thing I want to show is sometimes, depending on your data set, it could be a little hard to see if your distribution is normal or if normality is a reasonable approximation. There's something called a normal probability plot that actually allows you to compare what a perfectly normally distributed data set would look like against your actual values. And to do this, we actually use SciPy. I'm just going to copy and paste the code here because you won't actually see us do this too often throughout the course, but I do want you to know it's available to you in case you're interested in doing it. People who are coming in from academia or are used to the R programming language are probably used to this normal probability plot. But what it does is it compares your quantiles to the theoretical ones if it was normally distributed. So what we do here is we import SciPy as SP, we create the PLT subplots, and then it automatically creates this probability plot for us. And we can pass right here our test residuals. Go ahead and plot it, and we get a plot that looks like this. I'm going to zoom out just a little bit so we can see this full plot. But essentially what this is showing you is the red line is what a kind of normal distribution should look like. Obviously, when we're dealing with real data sets, our residuals are not going to be absolutely perfectly normally distributed, but they should more or less fit along this line. Where you may have trouble is towards the extremes. So if you start seeing these blue dots really diverge from this red line at either point or even in the middle, then again you know that there's an issue with your data set because the residuals are really skewing way off a normal distribution. So just keep that in mind that this is a toolkit for you in case you're having a little trouble reading the direct distribution plot. We don't have that many points in our test data set, so this distribution plot is not super indicative of anything. But again, the main plots to look at are the residual plot themselves. Okay, again, residual plots should look random, no clear curve on this, in order to understand that the data set is a valid choice for linear regression. Thanks, and I'll see you at the next lecture.